Let's spend today doing a few examples. So we'll start with, here's a polynomial, let's find all the zeros. And we can do that through synthetic division. And then once we've done that, we can express f of x as a product of its linear factors. And that will just mean factor f of x. So to start it off, we'll set up the synthetic division. And we're looking for a number in the box that will get us 0 at the end. And to start it off, why don't we consult the rational roots theorem? So we're going to look at all the possible rational roots. So P, all the possibilities of integers that go into there, that's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Then we go to Q, all the possible integers that go into 4, so that's going to be plus or minus 1, plus or minus 2, and plus or minus 4. Then, all of the possible rational zeros of f are going to be a number in here divided by a number in there. So we'll start 1 divided by 1, then 1 divided by 2, then 1 divided by 4. Then 2 divided by 1, then 2 divided by 2 is already there, 2 divided by 4 is already there. Then we go 3 divided by 1, then 3 divided by 2, then 3 divided by 4, 4 divided by 1, 4 divided by 2 is already there, 4 divided by 4 is already there, 6 divided by 1, 6 divided by 2 is already there, 6 divided by 4 is 3/2 already there, then 12 divided by 1, 12 divided by 2 is already there, 12 divided by 4 is already there. Cool. So that is the list of all of the possible rational roots. So we'll start with 1. Now, there's a little bit of a trick. It turns out if you plug in 1 for all the x's, you just get the coefficients, right? Because x to any power is just 1 at that stage. So if those coefficients add up to 0, then you know that 1 is a 0 of f of x. So you can quickly check. That's negative 20 plus that is 17 plus that is 26 minus that is negative 6, and it does not come out to 0. So you don't even have to try plugging in 1. You know it's not going to work. So the next number I'm going to try is negative 1. So we'll go 4, negative 4, negative 28. Multiply. That's kind of big. It's 63 times negative 1. That gets me negative 54. Then multiply by negative 1. And add that together. That should be 22. Subtract 22 gets me not 0. Okay, so negative 1 is not going to work. The next number I'm going to try is going to be 1/2. So I'll cross these out and go to 1/2. So 4 times 1/2, and that gets negative 22. Negative 22 times 1/2, negative 11. That gets me 26 times 1/2 is 13. It gets me 22 times 1/2 is 11. Now that is negative 21, which unfortunately gets me negative 21 over 2. And that does not add up to 0. Okay. Time for negative 1/2. So 4 times negative 1/2. Add them up, negative 26. Times negative 1/2 is 13. Add them together is 50 times negative 1/2. Add them is negative 16 times negative 1/2. Add them together, negative 24 times negative 1/2 is 12. We found one. Okay. So from here, I recognize that everything has a 2 that can be divided out of it. So why don't I divide everybody by 2 immediately? 2, negative 13, 25, negative 8, and negative 12. I can cross out this row, and that's what I'm dealing with. Okay, so now at this stage, this 2, the number 4 can no longer be a value of q because 4 does not go into 2. So I can actually cross out the 4 right there, which means I can cross out anything with a denominator of 4. Before I go on, I should try negative 1/2 one more time just to check, right? Because you can have a 0 with multiplicity 2 or higher. So here comes. 2 times negative 1/2 is negative 1. Add them up. Times negative 1/2 is 7. Add them up. Times negative 1/2 is negative 16. Add them together. Times negative 1/2 is, it worked again. So I have the 0 with a multiplicity of 2 currently. It happened twice. Now I go down here, and I can divide everybody by 2 again. So I'm going to say 1, negative 7, 16, negative 12, cross out this row. That's what I'm dealing with. Now that I have 1, I can no longer have a q value of plus or minus 2, because 2 does not go into 1, so I can cross this out, which means everything with a 2 on the denominator is out. So I don't have to check -1/2 again, because I eliminated it from my list. Okay, so now I have a much smaller list of things to try. Why don't I try 2? So I'm going to try 2. 1. Go to 2, that's -5, -10, it's +6, sorry. And then multiply by 2 is 12. It worked. Okay, now here I'm down to a quadratic. So I can immediately write down x squared minus 5x plus 6 and recognize that that is factorable to x minus 2 and x minus 3. And even if I didn't recognize that, I could do the quadratic formula, let this equal 0, and then get my zeros there. So what I know, I'm going to say the zeros of f. I found -1/2 and 2. So -1/2 and 2. And then I found another 2. Why am I saying 2 here? Because if I were to let this equal 0, right? I can say let 0 equals this, which means 0 equals that, which means I would get x equals 2 or 3. These are the zeros, because plugging in those numbers here would get a 0 here, which means I would get a 0 for f of x. Okay, so my final zero, is 3. And if I want to indicate multiplicities, I can say this one has a multiplicity of 2, this one has a multiplicity of 2, because they show up twice each. And then finally, when I write the linear factorization of f, this is saying express f as a product of its linear factors. This is what I'm going to say. I'm going to say f of x is equal to, this is going to give me a factor of x plus 1/2. And then this is going to give me another one of the same factors, so I can put a squared right there. And then I can write, for the next factor, since I have a 0, that's 2, my factor is x minus 2. And since that one shows up once twice, I can put a 2 here, and then x minus 3 corresponding to my last factor. So notice, the multiplicity of the 0 corresponds to the power of the factor. Last step. There is a leading coefficient of 4, which I must put right there. And that is the linear factorization of f. All right, brand new function. This time, we are given one of the zeros, and it's not real. So what we're going to do is we're going to start with this synthetic division setup. But before we even think about rational roots, we're going to use the 0 that was given to us. And so when we do synthetic division, the 4 comes straight down. 4 times 1 minus 3i is 4 minus 12i. Then when you add these together, the -8 and the 4 add up to make -4, minus 12i. Okay, from here, I actually have to start being careful with how I multiply. So I'm going to go ahead and write these things out. So I'm going to say, use this space, -4 minus 12i multiplied by the number up here in the box, 1 minus 3i. So what I'll get, -4 times 1, and then -4 times -3i, which is positive 12i. This is going to be -12i. And then -12i times -3i is 36i squared, which is -36. So very nice. These cancel each other, and I simply get -40. Okay, so -40 right here. Add them together is -2. That times 1 minus 3i is -2, right, plus 6i. Then the -2 and +2 cancel, I get regular 6i. And then 6i times that is going to be 6i, and then -18i squared, which is positive 18. Then I add these together, I get 2 plus 6i. Final stage, I'll take 2 plus 6i, multiply it by 1 minus 3i, and I'll get 2 minus 6i, then plus 6i, and then times -18i squared, which is positive 18. these cancel, and I get 20, which is exactly what I was supposed to get. Okay, then from here I say, well, I know by the complex roots theorem that if this is a 0, then the complex conjugate, 1 plus 3i, is also a 0. So let's do this. The 4 comes straight down. 4 times 1 plus 3i is 4 plus 12i. All of this adds up to 0. Very nice. 0 times that is just 0. Add them together is negative 2. Negative 2 times that is going to be negative 2 minus 6i. And the 6i and minus 6i cancel, right? This is what should happen. When you use the complex conjugate, your next line should have no imaginary numbers in it. So, negative 2 times that, negative 2 minus 6i gets me a very nice 0. Then I get to here and say, okay, well, why don't I divide everybody by 2? So it's 2, 0, negative 1, negative 1. And I realize they add up to 0, right? Now is the condition for saying, why don't I just use 1 here? So 2 times 1, add them up. 2 times 1, add them up. And then 1 times 1, and it works. So the rule is, if the coefficients add up to 0, then 1 is a root. Now I'm down to a quadratic, which means I can just let 0 equals 2x squared plus 2x plus 1. Because I looked at this and I realized I probably can't factor that easily by hand. So I'm going to use the quadratic formula, negative 2 plus or minus the square root of 2 squared minus 4 times 2 times 1. All over 2 times 2 is 4. So x is equal to, that's negative 2 plus or minus, here we have 8. So 4 minus 8 is negative 4, so the square root of that is 2i all over 4, which is, divide each one, and I get negative 1/2 plus or minus 1/2 I. Those are my zeros. Okay, so if I were to list them all out, I would say the zeros of G are going to be, from the top, 1 minus 3i and 1 plus 3i. So I can say 1 plus or minus 3i. And then my next one was just going to be 1. And my final one, I have negative 1/2 plus or minus 1/2 I. And there are all my zeros. Then finally, the linear factorization. This is going to say, list out all of the linear factors of G. So I have an x minus that. So I would write this as x minus 1 plus 3i, because I'm subtracting the whole thing. My next factor, x minus 1 minus 3i. And then for my next factor, I will have x minus 1. And unfortunately, I'm about to run off screen, so I'm going to write it right below. I'm going to have x minus each of these. So I'm going to have x minus negative 1/2. So I'm going to put plus 1/2, and then minus the 1/2 I. And the final one is x minus a negative 1/2 minus a negative 1/2 I. So that's what I'll have. And then finally, my leading coefficient 4 is just going to come out here. I apologize for the presentation. Imagine it's all in one line. I just ran out of room there. Let's do a similar one to the last one, but with a twist. So we have an unknown fourth degree polynomial with real coefficients. That's an added constraint. And we're going to look for the linear factorization of this form. So we know there's a leading coefficient, and then we have 4 linear factors because we have a fourth degree polynomial. Now, if we start filling in the factors using zeros, that's going to be x minus -1. That's going to be x minus 3. And this is going to be x minus all of that. So I'm going to flip the sign and get this. Now, it looks like we're missing one factor. But remember, the complex roots theorem says if you have a polynomial with only real coefficients, then if you have a non-real root, the complex conjugate root 1 plus 2i also works. So you would say this is x minus 1 minus 2i. And all we have to do now is find a. So we're going to use that information by saying if I plug in 1 for all the x's, then I should get -4 on this side. So I should get a times 1 plus 1, 1 minus 3, 1 minus 1 plus 2i, and 1 minus 1 minus 2i. Now, the setup is not so bad because 1 minus 1 just cancels itself out. 1 minus 1 cancels itself out. So we really have -4 is equal to a times, this is 2 times -2 is -4. And here I have 2i times -2i, which is -4i squared, aka positive 4. So then I just say, oh, this is -4 is equal to -16a. Divide the -16 over, I get a is equal to 1/4. From there, I can just say j of x equals the 1/4 that I needed to know, and then the rest is just writing out the linear factorization. There we have it. All right, let's do just one more. This time we have a fifth degree polynomial with real coefficients. So we'll go k of x equals, we have the leading coefficient, and then we have 5 factors corresponding to the degree of 5. And so we know our first 0 is 0. So I can write this as x minus 0 or just as regular x. This next one I have x minus this whole thing, which makes it plus 1 minus 3i. And the complex roots theorem says if I have this as a 0, then I have the complex conjugate as a 0 as well. So this gives me x subtract this whole number, which gives me plus 1 plus 3i. Then I go over here, I have x minus 2i as a factor, and the complex conjugate of this is negative 2i, right? So 2i is kind of like 0 plus 2i, which means the complex conjugate 0 minus 2i. And then we take this, x minus that gets me this. All right, kind of obnoxious looking, but not a big deal. We can plug in -1 for all the x's and get 18 on this side. So we'll say 18 equals a times, this is going to be -1 minus 0. -1 plus 1 cancels out and gets me minus 3i. -1 and 1 cancels out, gets me positive 3i. And then here we have -1 minus 2i and -1 plus 2i. Then we go and we keep simplifying. So this is going to be a times, we'll keep it -1 here. These two multiplied gets me 3i times 3i with a negative in front. So it's -9i squared, which gets me positive 9. And then here, what I'm looking at is an a minus b, a plus b, difference of squares. So if I take that squared, I get 1. Then I go minus, and if I take that number squared, I get 4i squared. And 4i squared is -4, so 1 minus -4, this whole thing comes out to be 5. Okay? So I'm looking at 18 is equal to -9 times 5 is -45a. So a is 18 divided by -45. And since a 9 can go into both of these, simplify the top becomes 2, the bottom becomes 5. I get -2/5. So overall, my final answer will have k of x equals, this a value we found goes into the a, -2/5. And then instead of writing x minus 0, I'll just write x. And then we keep going. That's going to be x plus 1 minus 3i. The next factor, x plus 1 plus 3i. And then the next factor is x minus 2i, x plus 2i. And there we have it. That's the factorization of k of x. All right, you guys take care. Good luck. Study hard.